Good morning. Today I would like to present our recent joint results with Peter Rickaski on a universal sequence of tensors for the asymptotic rank conjecture. Let me recall that tensors appear prominently in mathematics. Abstractly, we just define them as elements of a tensor space. Thus, we take a tensor product of several vector spaces, and we call a tensor an element of such a space. As such, tensors are generalizations of vectors and matrices to higher dimensions, and they form a space of k-linear maps where k can be greater than 1. We know from basic algebra that we can regard a matrix as a linear map. If we have a 2-linear map, 3-linear map, that's a tensor. There is also a way to look at tensors of high order as linear maps where domain or codomain or both are tensor spaces. Now, I would like to emphasize that there is a difference whether we think about a tensor as a multi-dimensional array filled with numbers, or if we think about it simply as an element of a tensor space. It's very similar to matrices, where a linear map is not formally a matrix. To make it into a matrix, we need to fix bases, and exactly the same is true for tensors. We can see it well in computer science, where tensors correspond, for example, to bilinear algorithmic problems. What do I mean like this? Let us consider matrix multiplication. Well, here the task is given two n by n matrices to compute the product of those matrices. This is a problem in basis. We can also think that we are given two linear maps and we want to compute their composition. So here we can represent a complicated tensor associated to this bilinear map. So for fixed n, multiplication of two n by n matrices is just 1 point in a tensor space. It's just 1 point. And we can ask how to represent it, either in a basis, where it is quite easy to view it as a multidimensional array, or more abstractly, when we want to represent it as a sum of rank 1 tensors, that is, tensor products of vectors. And it turns out that the second representation as a sum of rank 1 tensors gives us an algorithm. And we can access complexity of this algorithm by an intrinsic notion associated to a tensor, namely tensor rank. So tensors, abstractly, we can think as algorithmic problems, but representations as sums of rank 1 tensors give us algorithm, and tensor rank is the complexity measure for matrix multiplication. Now, of course, often we don't want to fix n, and we don't want to simply focus, for example, on multiplication of n by n matrices. And for this reason, a very important notion is that of asymptotic rank, where we take Kronecker powers of a tensor. This is like tensor product for a 3 tensor, but we bracket the vector spaces together so that a Kronecker product of two 3-way tensors is still a 3-way tensor. We look at ranks, and we take the power to 1 over n, and we take a limit as n goes to infinity. Such limits exist, and this is known as the asymptotic rank of a tensor. In general, it is very hard to say what is asymptotic rank of a tensor, and even for 2 by 2 matrix multiplication, it turns out that this notion captures the whole complexity of multiplying n by n matrices. So very precisely, it's quite easy to see that the asymptotic rank for of a tensor representing multiplication of 2 by 2 matrices is 2 to omega, where small omega is a famous constant in complexity theory. Namely, one defines omega as the infimum of numbers such that one can multiply two n by n matrices in time n to power omega plus epsilon for every epsilon. Okay, now for arbitrary tensors, they can live in different spaces. They can live in CD, tensor CD, tensor CD. And of course, we expect values like rank, border rank, asymptotic rank to be larger, where D is larger for general tensors. And hence, it turns out that if your tensor does not really live in a smaller space, the important invariant is not maybe even the asymptotic rank of the tensor, as rather a logarithm with of base D of the asymptotic rank. And then we can notice that this number is always between 1 and 2. So we can ask, what are the worst complexity problems? And first we would like to associate numbers that tell us what is the worst situation that can possibly happen. So for a fixed D, we can ask what is the worst asymptotic rank. However, instead of remembering the asymptotic rank, we simply remember the logarithm with base D, because we want to have a number that is easier to compare as D changes. In this setting, a conjecture that is often attributed to Strassen, although Strassen used to present it under additional assumption, is that we are in the best situation that one can hope for, namely that there are no hard problems among tensor problems, one could say. That is, that always this exponent here that we get is equal to 1. So it's not close to 2. This conjecture would immediately imply such things like omega equal to 2. So first, let me say our theorem that actually as D goes to infinity, the limit of those exponents exists and is equal to the supremum. This means that there exists a God-given constant which governs all, even big tensor problems. And you may know the constant small omega. So due to Strassen, there are known results, namely that this limit is greater or equal than omega half and smaller or equal to 2 omega divided by 3. Thus, this universal constant is clearly related to omega. You may think that it's equal to omega half, but it's not so easy to prove it. So please notice that even if we know everything about matrix multiplication, meaning that we could prove the famous open conjecture that small omega is equal to 2, we still would have a gap and would not know this universal constant. Now, how could we try to access it? Well, the important thing through the definition of asymptotic rank is a map known as the Kronecker power. It takes a tensor, a three-way tensor, and as I said, it builds a tensor that normally should live in a tensor product of many CDs, but we bracket them together. So the space C to D to P should be thought of as tensor product of P spaces, each one equal to C to the D. So we have this Kronecker power map. And please recall that the asymptotic rank of a tensor T essentially means that we have to understand ranks of this Kronecker power. Now, let us write it in coordinates, not so abstractly. So I take any tensor. Remember that the basis of a space C to the D is given by tensor products of 3 basis vectors, and then I put arbitrary coefficients lambda ABC. So here, ABC are numbers that go from 1 up to small d. Now, the Kronecker power of this tensor needs to be something in a basis. So before I will tell you what is this question mark, let me tell you how we should think about the basis of this big tensor space. Well, we need to pick 3 basis elements of the space C to the power d to p. Now, if we just have C to d, then a basis element is like a number from 1 to d. So how do we cook up a basis of d to p? Well, it should be a sequence of length p of numbers from 1 to d. And we pick such 3 sequences. It is also good to think that the basis of such a tensor product is actually indexed by 3 by p matrices filled with numbers from 1 to d. Yeah, so you can imagine that this is actually a 3 by p matrix, where this is the first row, this is the second row, and this is the third row. Okay, so now we ask, what is the coefficient in front of such a basis vector? And if we do the tensor product and then the Kronecker product, we see that this is simply a product of the coefficients of our tensor, where we first take the coefficients indexed by A1, B1, C1. Then we multiply it by a coefficient indexed by A2, B2, C2, and so on. Hence, it is simply a degree P monomial in the original coefficients of our tensor T. And it's not hard to see that we will get all possible monomials of degree P. However, for different basis vectors, we can get the same monomial. Namely, if we think about this as a 3 by p matrix, we can permute the columns of this matrix, and this is like changing the order of the variables in this monomial, which clearly does not change the product itself. So it's natural to group the basis vectors according to the monomials they get. So instead of taking a sum over basis element, we take the sum over all monomials of degree p. We take a given monomial evaluated at the coefficients of t, and then this t to g is the sum of all basis vectors that get as a coefficient the monomial represented by small g. So those TGs are very easy explicit tensors. Their entries are simply 0 or 1. And again, if you are thinking about the coordinates of the big tensor space as 3 by p matrices, then we fix one such matrix and we put 1 on all coordinates corresponding to column permutations of that matrix, and there we put a 1. Okay, so they are really explicit in every sense of computer science you can think of. Now, KDP is the Kronecker map. However, in some sense, we can think that this is just a map given by all degree P monomials. Such a map in algebraic geometry is known as the Veronese map. If we repeat it every monomial once, and the linear span of the Veronese map is then just the whole space. But as we are repeating coordinates, we can see that our tensors TG form actually a basis of a linear span of the image of the pth Kronecker map. And in algebraic geometry, we are used to the fact that the linear span of the Veronese has dimension as big as possible, which could be considered a bad thing. If we have d to the third variables, then the dimension of the linear span of the Veronese is a binomial coefficient d to the third plus p minus 1 choose d to the third minus 1. It looks like a huge number, but please remember we should think that d for now is fixed. We simply want to understand a tensor in a tensor space. And then this binomial grows as a polynomial in P. The dimension of the linear span of the image of the Kronecker map is a polynomial in P. This may sound as a trivial fact, however, it has far-reaching consequences. Namely, if we take simply sums of our tensors Tg and adjust P properly, it turns out that we get an explicit sequence of tensors whose rank governs all ranks up to a polynomial in P of all Kronecker powers. Yeah? So we have a space of dimension that is polynomial in P, but the ranks of the tensors in this space in principle grow exponentially with P. So when we will be taking power 1 over P, this polynomial factor will not play a role. And indeed, we can realize this universal constant, which is a limit of the worst exponents, simply by looking at the asymptotic rank of our explicit tensors, which exhibit the worst possible case. So I would like to say that there are two very hard things. One is deciding if extended Strassen conjecture is true. That is whether every single exponent is equal to 1. So the asymptotic rank of concise tensors is simply the size of a tensor. That's very hard conjecture. As I was already mentioning, for example, confirmation of this conjecture would imply that small omega is equal to 2. There is another very hard task. We cannot produce explicit sequences of tensors of large rank or border rank. In fact, we don't know how to make the growth of rank superlinear, and it's even worse. We cannot produce tensors that are explicit, sequences of tensors in N that are explicit in the sense of computer science, of rank greater than 3n. So we don't know how to prove that the given sequence of tensors in Cn, tensor Cn has rank above 3n. However, our results say that there is a very easy winning OR. That is, if extended Strassen's conjecture is false, that means there actually exist hard problems among tensors. For example, matrix multiplication is really strictly harder than matrix addition, and we cannot do it in time n to 2 plus epsilon for every epsilon. This means that the sequence we have just provided, this sequence, actually needs to have superlinear growth of rank. And this is a very explicit sequence. So either you trust Strassen conjecture and everything is simple, or the sequence I have provided you exhibits, in some sense, the worst possible and certainly superlinear growth of rank behavior. Okay, so what are more explicit results that we get? So one can obtain different bases, not only the one I have given of the linear span of KDP, so the Kronecker map, and every such basis will give us an understanding of all tensors and their asymptotic ranks in CD, tensor CD, tensor CD. Thus, if you have your favorite basis and you can control the rank of it, then you can answer things like extended Strassen's conjecture. And how could you use it in practice? Imagine you found a subset S of tensors, and you know that there is no polynomial of degree p vanishing on S. It could be, for example, a high secant variety of the Segre, so of rank 1 tensors. then this fact that there are no polynomials of degree p vanishing on S is exactly equivalent to the fact that your S spans the image of the Veronese, or what is more interesting for us, the image of the pth Kronecker map. How to apply this in practice? Hauenstein, Ickenmeyer, and Landsberg proved that the generic rank in C7, tensor C7 is 19. However, the secant variety, so tensors of border rank 18, form a hypersurface, and the defining equation of that hypersurface has degree at least 187,000. So this means that until we reach 187,000, there are no polynomials vanishing on this hypersurface. And this, just through this easy observation that I have given, allows us to give an upper bound on the asymptotic rank of every tensor in this space, C7, tensor C7, tensor C7, and this bound is below 19. It's actually very, very close to 18. And this is just an example. I am sure there are many more applications of those observations I have just given. In the last remark, I would like to say that there is a more representation theoretic approach to Strassen's conjecture through our results. Namely, please remember that I told you that you can permute the columns of the 3 by P matrix, which and such an orbit corresponds to the tensors Tg that we would like to understand. This gives a hint that the action of a symmetric group with P elements should play a role in the conjecture. And indeed, one can show that different bases of the space we are interested in could be given by SP invariants of a triple tensor product where alpha, beta, and gamma are partitions of P, and S alpha, S beta, S gamma are Specht irreducible modules for the symmetric group representation on P elements. Thus, if one can understand the ranks of such tensors, one has in principle access to Strassen's asymptotic rank conjecture. The result is slightly more explicit. That is, if we want to understand tensors in CD, tensor CD, we just need partitions of P that have at most D rows. And this would be very interesting already for D equals 3. And one can say, oh, maybe there is nothing interesting about those tensors. However, our results are essentially if and only if. Thus, the non-trivial bound on the exponent 2 omega divided by 3 tells us that this invariant tensors need to have rank below the generic rank. So there needs to be a better than a naive estimate for ranks of those invariant tensors. Thank you very much.